Yogah Karmasu Kaushalam.
Dear friends, today is the second lecture of myself in the refresher course. The title of the talk is Digital Signals, Use of Digital Technologies, Future Application Areas like Internet of Things, Machine Learning, Artificial Intelligence, Robotics, Drones, Image Processing, Fiber Optic Communication, Satellite Communication, Radar, etc. And the use of all these technologies in making our life easy. So, this is a longish kind of a title, but it tells us in short what are the technologies available today and how these digital technologies are helping us to revolutionize our life, revolutionize our lifestyle, and all that goes with it. So, as regards this material in this particular talk, first of all, what we have studied up till now in the last lecture, we have tried to study what makes a digital signal, how analog signals are converted into digital binary signals, and number systems, the counting process which counts the number of clocks, and what are the requirements of digital signals. Now, using different kinds of techniques for converting analog to digital, uh, we have also tried to study that. Now, we have seen one more thing, that small ICs with a small number of gates, individual ICs, doing a particular job, and then assembling them together to make a system is very cumbersome and very difficult. So, this does not go very far. So, new technologies, new requirements of today does not allow us to use small circuitry. So, what is required? The main thing that is required is in a single chip, we should have millions of ICs and millions of gates, and those gates should be of a general purpose. And from those gates, using software, we should be able to make systems. And this particular big circuitry in a chip with millions of transistors, which is very small size, should be attached with many peripherals. So this is how the microprocessor and microcontrollers have been born, and they include many external gadgetry, external devices, external small circuits which are attached to them to make the complete system which is successful and which delivers in the present day. The students of this department who have done MPhil and PhD in this area have developed such circuits and have used such microprocessors and controllers, and thereby the new type of technologies have been utilized, and this is the way for the future. So most of the simple small circuit IC and all other thing is now obsolete, and with these microprocessors and controllers, these are the only uh, devices which will be used in future, which will contain hardware and software combined, which will require the knowledge of IT and also the knowledge of software and hardware, and then and only then real time applications will be possible. The list of applications I have shown you over here, and we will try to cover them in these next few slides. Now, first we are going to look at a program made in EMRC where a 2-bit and 4-bit ADC has been fabricated by myself in the department, and we are trying to study the performance of 2-bit and 4-bit ADCs, which we will see the experiment being performed and which will give us a lot of insight into how digital signals are fabricated. Dear friends, now we will look into a few important applications, and these all applications are possible only because of all these technologies have converged as of today, and practically these applications are available today. These are day to day experiences of all of us, and they have brought a huge amount of revolution in all our lives. Digital communications, internet, banking, railway, huge networks. These huge networks are possible because of digital communications. On internet, you get any information anytime you want from anywhere around the globe, and it is affordable and not very costly for a person to access to that information. Secondly, banking. Banking sector is a huge sector throughout the world. You could not think 10 years back that you will be able to get money without going to bank. Today, there is no need of a money also. Everything is done through cards or even online with your mobile. So you don't need the bank at all. No physical currency is required. So that level of confidence in our banking system is there. Then railways has got a huge network throughout the country. You get reservations, you get booking, and they are all perfectly safe. Your money is refunded. All things are possible wherever money transaction is involved, and if that is possible to do for millions of people, it is a great achievement. Similarly, is the story of hotel booking. Same is the story of aeroplane booking. Same is the story of getting food on the railway at a particular railway station. So these all things instantly are possible today with the use of this digital technology. Your mobile phone, what it does and what it cannot do. I can say it does everything you want. It does your banking. It brings grocery to your house. It brings food to your house. It brings clothes to your house. You can do any damn thing. You can order things, they will be delivered to your house. You can see the things on the internet and you can place the orders. If you are not satisfied, the things are taken back and new things are supplied to you. So everything, exchange of material is also possible. So all these things are possible using the cell phone. Photographs, pictures, multimedia, your Facebook, television, all these applications and printing technology are possible today. Today you can think of printing a single photograph. You can think of making a single election banner or making a picture, single picture. Once upon a time, you need at least 5,000 copies to be printed. Otherwise, physically, it was not possible to have a single print affordable. Today, it is affordable, and you can superpose pictures on each other. You can play fun. You can do whatever you want. And with the digital technology in the mobile, you have the pictures. Next minute, you want to delete them, you can delete them. No cost is involved. No need of printing also, and you can communicate with each other very easily. Entertainment industry, music, CDs, VCDs, DVDs, films, animations, all things are possible today and very affordable by the digital technologies and all these technologies together. Robotics in industry and medical field, this is a very gigantic application nowadays. In industry everywhere, robots are used to do their many activities. So many people can be lazy and be happy at home, and the robot will do the job. It doesn't make any errors. Robot can make food for you. Robot can make chapatis for you. Not only that, robot can prepare pizzas, and they all will be of the same size. There will be no errors. And your house, you stay somewhere else, at the time before going to the house, you press some buttons or some through the mobile, your door will open for you automatically, your fans will open automatically, your TV will start, your cooking will also be made automatically. All these things, cooking vessels will be cleaned, everything, your house can also be cleaned. Such Alexa type of robots are being used regularly in our houses in India also, that has come. So it is affordable to millions of people, not only throughout the world. And these all things are possible with, means, mechanically also, and medical field. For a particular person, drug delivery is there for a particular person at his particular place, and for that delivery the sonography or other kind of gadgets accurately, endoscopy, so you don't need to cut a person, no need of any wastage of your blood, and the drug is delivered in a very minute quantity to a particular place, and you can save lives. So this also, personalized medication is going to be the future. Fast calculations and mathematics, the computers and supercomputers are there. They break up your problem by using algorithms into parallel processing, and you can do things very fast. So such kind of applications are there where you require fast calculations and real time output and real time signals to control the systems. Second order, third order control systems are possible today extremely fast. In satellite communication also, such kind of fast mathematics is required, otherwise it is not possible to survive in today's world. And those all things are possible because of fast digital systems. Intelligent gadgets, toys in day to day life are also there today. And finally, future technologies, Internet of Things, artificial intelligence, machine learning. All these things are possible. We are talking about few hundred years back. H.G. Wells, in his famous book Time Machine, has professed that human beings will have only two thumbs. All our thumb, our fingers will vanish, and only two thumbs for pressing two buttons. That's the end of the story. And his prophecy is coming true. Man will sit, he will be lazy, he will do nothing. And today, with this Hawkins, the famous person, we have seen, with chip implanted into his brain, we can think, and accordingly we can give signals and things move physically. That is today possible. And you can have clones of human beings, true copies, and clones of armies, and human being will be reduced to a number. Today Aadhaar card number is all that, your identity. That all things are coming true, and that what he has said about the future is coming true. But this is not the end of the story. Artificial intelligence means machine will start learning, computer is already learning, computer is making faster and faster things, computer is playing chess with human beings, and it is making all our best chess players lose matches with the computer. So it is faster than human beings, faster than what we can process. But it is also dangerous for human beings. We have seen many such movies very recently, like Krish and Discovery, Dinosaurs. Such fantastic movies are coming which talk about fantasies, but which are most likely to come onto the planet very shortly. Unless and until we are able to overpower the computer, this artificial intelligence will may try to distract our lives. That is one danger. And second thing, we need not be all that afraid. Don't worry. In defense industry, a lot of artificial intelligence and these things are being used already. And we are talking about cloned armies. They are already there. And drones are there. Drones are having a lot of positive applications, like in agriculture and robotics and industries. And drones are having other applications in missile technology, other applications in bombing using atom bombs, and such kind of danger to the humanity is also there. But don't be afraid. They have tried all these instruments in the Ukraine war very recently and earlier in the Iraq war, but the target hitting is not very accurate. Still, lot has to be done in order to make these fantasies come true. So there is still hope for human being, but human being has to overpower these things. Now, the last and most important thing which I want to emphasize in my talk is obsolescence. What is this obsolescence? Whatever I have taught you or explained to you, this digital electronics up till now is already obsolete. Obsolete means old, trash, useless. Because using small ICs, no circuits are made now. Only processors and controllers with millions of ICs are made. And much of this technologies which we talked about, much of what we talked about accuracy, what we talk about errors, what we talked about the resolution, this is all for understanding logic and it is for our understanding of the subject. It is a basic fundamental logic understanding, but these all things are no longer required. They are obsolete. That is a textbook knowledge. It is easy to know as a history that these are the ways of finding the solution. But today in life, the technologies have been fast, much faster. So today you get a perfect communication, you don't have any errors, resolution problem is not there, your memory problem is not there because you have got infinite memory, you have got infinite good resolution, you have got faster and faster devices, memory storage is also huge. So these all problems are not with us, they simply don't exist. Just like we are born with a golden spoon, we are born with all these technologies and all these gadgets are available, we can take them for granted because they are going to work perfectly. And in communication technology, finally, as an academic interest, again for academics purpose, I will explain to you in a very small nutshell about the fundamental difference between error quantization and digitization. The fundamental difference between analog and digital signals or communication which exist as of today with all today's technologies. The difference is in analog communication, analog signal, the signal can vary continuously. There can be any change in the signal, there can be any error in the signal, and that error propagates throughout the system. You cannot calculate that error, you cannot stop it, it is unknown to you. But in digital electronics, once you convert analog to digital, you know what is the quantization error. And that error you can reduce as much as you want. And you don't need it too much. Why do you want 100 bits? You don't need. Your for your particular application, if 10 bits is enough, you use only 10 bits. You will not use the 100 bit accuracy. So that much technology is available which will not have any error. So that much error is we can withstand with that error. So when your things are slow, when human response is slow, you don't need to go to that resolution, that accuracy. So most of this knowledge, because in digital electronics, quantization error is known to you. Depending upon the resolution, you can exactly calculate. And the beautiful part of it is, as the signal propagates, because it is a square wave, and because you are sampling exactly at a particular point in time on that square time pulse at the center, and with mathematics you can convert and confirm at any point in time along the communication. If you get the signal, you can reconstruct the original square signal as it is without error. So that is the beautiful part of it. You can remove the error 100% and get the original signal, which is not possible in analog communication, which is possible in digital. And today our eating chapati speed is, you eat 4 chapatis in 15 minutes. You cannot eat 50 chapatis in 5 minutes. That's physically not possible. So at that speed, if we eat, it is enough for us. We don't need more speed. That kind of speed, that kind of cloth, that kind of communication is possible today. So most of this is only for our understanding, but otherwise the beautiful part is digital signal can always be reconstructed. That is the beautiful part of the today's technologies, and therefore it has made our lives simple and easy. We discuss now the output of the spectrometer experiment conducted using microcontroller. The spectrometer, the light that is available from red, green and blue or from white light, will through the lens and through the grating and through the system will be incident on the processor sensor, and we get this type of output. Here lines are marked. You bring your pointer to this line, and then its intensity will be available on the y-axis, and we will be able to find out the particular lines, their frequencies and their response in terms of intensity on the at the output of the instrument. So this kind of work is very useful for analyzing the light coming from different LEDs. Not only that, from this experiment we are able to study what are the molecules or the atoms which go into making the particular light. We are able to understand and study the response of different minority carriers uh, in the given type of semiconductor. So such studies can be conducted using this kind of a spectrometer. Now the radar systems. Various types of radars are there which are made possible using the digital technologies. The airport control radar is a radar which transmits a beam of light or also at other frequencies signals to the pilot, and pilot responds. So this radar tries to find out the object, that is the aeroplane, its speed and all the details available on the screen at the control tower, and the speed of the aeroplane, the direction of its motion, etc., is available and calculatable. Another type of radar is used for research systems, and it is mesosphere, stratosphere, troposphere radar called MST radar, and such MST radars are very few in the world. One of it is installed at Tirupati Valley near the famous Tirupati temple, few kilometers away from there, in the valley where there is a minimum human activity and a big field of 32 by 32 Yagi antennas mounted in the field covering a square kilometer of an area, and this array of antennas are used to look to the sky, and a very big field of view is available, and this MST radar has got a huge power, and this radar array is able to send beams into the sky, vertical and at certain degrees, east, west, north, south. So such 5 beams are synthesized by applying signal to different radar elements in the array, individual antennas in the array, and synthesize and generate those beams and send huge amount of power in terms of megawatts into the sky. What comes down from the mesosphere, stratosphere, and troposphere in this region, there are no electrons and only atmosphere, and the density of atmosphere going down as we go up. So very less material over there, and whatever fluctuations or variations are there due to wind and other things have to be studied, and this radar will give us a handle on the monsoon and rainfall studies in the peninsula. And therefore this radar, costing a few hundreds of rupees, has been installed there, and the project is going on. Some 10 12 years back this radar was installed over there, and backscatter means very small amount of signal comes back from that region, and that is integrated and a three-dimensional wind profiles at a very high resolution, the speed of the wind, the direction of the wind, and so on and so forth, the complete profile from in the given region has to be obtained. So very powerful kind of a radar system has to be made. Then astronomy telescopes are actually passive devices. We only see the solar system, far objects in the solar system moving towards some galaxy and other galaxies, other stars through the telescope. So what we require? We require huge antennas covering a very large area or field of view, and then collecting all the signal over a long exposure time of days, hours, months, and all that signal uh, is a type of produces a image at the focus, and from that image, in terms of pixels, we select different small tiny areas and then study that, and that is how today in astronomy you can study many stars simultaneously. In the days of Copernicus, a small telescope is there. You point it to a particular object, you can study that object over 2 years, and your data is available only about one particular object. Now, with this image processing technology, with digital signal processing, with analysis, these technologies and huge memories, we are able to study a large field of view, go deeper and deeper into the sky, and using satellite borne or the telescopes which are above the atmosphere, that is in uh, say earth stations, satellites which are above the atmosphere, they get a much better and clearer picture of the surroundings or of in the astronomy, and much clearer signals are available, and we can study deeper and deeper into the universe. So these all possible provided you have huge memories, provided you have new technologies, and provided you have image processing capabilities. Warfare radars are totally different. Warfare radars also transmit, and but the object is non-friendly. The enemy plane does not want to identify itself. The enemy submarine does not want to identify itself. So they are coated with stealth paints so that they don't reflect anything. So they try to dodge you. They try to come to your targets at a very low angle so that your radar cannot detail them. Secondly, these objects try to change their speed and direction in order to avoid identification and in the war. So these unfriendly kind of things, to them you have to lock to the object and go on tracking the object, and depending upon the tracking as it changes direction and speed, similarly you will have to also pass on some commands to your ground based systems or airborne systems to fire those objects till before they enter and hit the target. So this is a extremely difficult kind of activity, but to a certain extent it is successful. To a large extent still we are groping. Means the Star Wars project of USA in the Iraq few years back has not been very successful. The project of Israel recently in the war, trying to create a dome, not a physical dome, but a kind of a cover over their area, inside which if any enemy entry thing enters, it will try to shoot it before it lands on the ground. That kind of thing they have tried. They have been more successful. This is just 1 or 2 years back. And nowadays in Ukraine also, in the warfare, such things are tried, but they are also not able to hit the targets as much as desired. So still a lot of things have to be learned. Then anti-ballistic missiles and drones. These kind of things, anti-ballistic missiles, these missiles are launched from a distance of supersonic intercontinental ballistic missiles. So they are launched through a kind of a fast moving rocket. They are controlled remotely. They change their directions. They move in zigzag or any other path, and they will try to hit the target. They are manless. Similarly, drones are manless, and they contain even nuclear warheads. So China is has such stations, such launching places from where they can launch easily up to Delhi. Our country has also got such capabilities like this BrahMos missile and other Nag missile. These missiles are able to hit the target at a very large distance. These these targets, before they hit, we have to shoot them in the sky. So it needs sending commands. It needs powerful and fast data collection and fast calculations and hitting the target, sending commands and physically hitting the targets. So this is an extremely difficult activity where fast calculations and decision making is involved, where the computers or supercomputers with fast digital data acquisition and analysis is required. But don't be so much afraid. Traffic on the road is our day to day experience. We are simple human beings. Using our two-wheeler or four-wheeler, we move on the roads. Ahmedabad roads are very much jam packed, and we are moving through the road. Suddenly, some monkey jumps. Okay, suddenly, some small boy rushes onto the main road. Okay, suddenly, some vehicle is coming in the wrong direction and at a good speed towards you. Under all these circumstances, we see rarest of rare type of accident happens. Most of the time, people brush through or they are just touch the vehicles, but they are not getting a major accident. Why? Because our eyes and ears are trying to gauge the speed of the other object. trying to see how it is moving, trying to see its acceleration, trying to see its direction of motion in all three dimensions. That person also applies his brake, he uses his steering, trying to avoid the accident. And all that system, our brain also works very fast within a reflex, fractions of a second. Our brain processes all this, gives command, and accordingly we change the speed and direction of our vehicle also. So this is not impossible. Only thing is, these applications which I showed, there the response has to be much faster. Using digital technology, data acquisition is much faster than what human can do. So that is the difference between the digital technology, and today we are having those technologies. Today it is possible. Some 30 years back these things were not possible because we don't did not have that type of radars development over in that time. Now, satellite communication is again another very big area of applications. On the satellite, there are passive cameras which go on taking pictures of the objects either in the universe or on the ground, towards the ground. And these cameras work in infrared, visible region, ultraviolet, various kinds of types of cameras are there. And from the image they acquire, we try to do the image processing or remote sensing and trying to get the information about the earth, about the water resources, many things. And there are active radars on the satellite. On the satellite, we have placed some transmitters. They transmit signals in the microwave region. And then whatever reflection comes, they record it. And from that recorded information, there again that kind of a radars are also used which are active, and the crop or the ground water or soil or mountains are not only identified, details are also available using active radars. This is all because of the digital technology and a fast designed response. In satellites also there are two kinds of major areas of work. One is geocentric satellite, which is used for TV channels and broadcast. Now, geocentric satellite means the satellite moves around the Earth, its orbit is 24 hours, and it moves in the opposite direction to which the Earth is rotating. So, always above the equator only at a particular point, wherever you decide on the equator, on that point it is always sitting there, that satellite. As the Earth rotates, this fellow also rotates. So, relative to the Earth, it is not moving, and it has a 24 hours time period, and it is a circular orbit. And this satellite has to continuously, you cannot give energy or power to this. So it is should not take power. So whatever small solar panels will be there and some energy will be there, that is used for communication purpose. You cannot move the satellite using energy. So it has to be under the gravitational force. So such a orbit happens to be geocentric with a circular orbit at a height of 36,600 kilometers from the Earth. Now 36,000 kilometers is a very large distance, and therefore if you find out this with the speed of light all this electromagnetic radiation is moving, it will take some time to reach such a large distance. And the inverse square law tells us as the distance increases, the energy is spread over the spherical region, larger and larger region, and therefore the density of energy available goes on reducing inverse square of the distance. So, because the surface is increasing, you have to put in huge amount of power for reasonable power to reach the satellite. Otherwise, communication will fail. So you need powerful transmitters on the ground to transmit energy. You need very good quality low noise receivers on the satellite, and you need again the signal that will come back will be very weak for such a large distance. So you will need a earth station which is huge and which has got very low noise, and it is able to collect the signal. You need huge antennas on the ground. On this satellite you cannot have huge antenna, that size is limited. So you have to work on such frequencies where these things are possible. Today, such antennas are possible to make, and we are talking in the terms of gigahertz range, microwave, high frequency microwave range. So, in that range, these signals are sent, and at the ground station, you receive them at the radio, at the Doordarshan station with a huge antenna and all that, low noise, special amplifier, and so on. And then you send it to the local people through the cable. Or if you want to put above your head in your house a big antenna at your house on the top of your house, then also you can receive such channels. So today those channels reception is also possible. Okay. The requirement of these satellites and their amount of energy, all etc. And you have to make huge communication, huge amount of signal has to be transmitted if you want to see a serial or a movie or a video. Video requires a lot of mm, information in terms of megabytes and gigabytes. So you have to stream them at a very high speed also. Then only you can see. Otherwise, what will happen? It will take a lot of time for the signal to be collected. Then you will be able to see the serial. You will not enjoy if it does not move fast. So what you have to do to see the real thing? You need a broadband. And so a satellite earlier with a 36 megahertz channel bandwidth, somewhere around 8 or 10 gigahertz uplink channel, another 8 or 10 gigahertz downlink channel, and a transponder of 36 megahertz for one single channel, one single video program. If you have something like 500 megahertz bandwidth for the complete signal to be sent up, you will be able to have around 12 channels for one satellite. So if you want to have 100 satellites, you 100 channels, you will need 8 satellites, geocentric satellites. Now, if you are able to increase this bandwidth instead of 500 megahertz to 1 gigahertz, then your channels will be doubled. So you will require at least 4 satellites above you. And to cover the complete globe, all the 360 degrees spatial, you will require minimum, ideally minimum 3, but reasonably some shadow area if you want to avoid and all that, some overlap if you want, you will require 4 satellites, and they will give you 8 channels. If you try to do something more, you may require to for, as I told you, for one single satellite, 4 satellites above the Earth at a fixed point, then you are able to cover the complete globe, and that will give you equivalent to something like 8 channels. And multiplied by 10, then it will get 80 channels if you have 10 satellites or 5 satellites into 4. 5 into 4 is 20. 20 satellites, 30 satellites, geocentric. That will cover the globe. Okay. So you can see the gigantic requirement for a geocentric satellite, and huge amount of power of duration stations and all that. Against this, for 100 channels. Now, against this, what are other alternatives today? Other alternative is, can you have low orbiting satellites? Low orbiting satellites means you bring them down. Don't put them at 36,000 kilometers. Bring them around 100 kilometers or 300 kilometers. If you are in this range above the atmosphere, so atmosphere trouble is sorted out. Ionosphere is much above, and ionosphere is transparent to these high frequency waves in the gigahertz range. So nothing to worry about ionosphere. So These satellites roaming around 100 kilometers will not be much affected, but they will not be in circular orbits. They will be in elliptical, highly elliptical orbits, and they will pass above your field of view within every 2 hours or 3 hours. So per day you may have 2 or 3 passes only, and the time period will be in terms of 2 hours, 3 hours, something like that. Because you cannot power them. So what you will do? So at any given point of time above you, in the field of view, you will require another at least one satellite there, maybe two, three, ideally. So a constellation of 100 such satellites, which will not collide with each other, and which will move at high speeds, and which will move near the Earth around 100 kilometers. If you have such a constellation, then you can at any given point in time you can see some 3 4 satellites above you, and they can contact with each other, and communication is possible. Today such constellations are also made for making weather studies, for surveillance, particularly military people want to get details, want to get high resolution information. This is all possible today. And if you see the internet, Google or anywhere, they give you GPS system, they give you your location, they can identify, you can identify people, you can identify your car, you can identify your house, you can identify the number on the car. So such high resolution thing is available in the open domain on the internet. Defense things are much better. So such constellation to study the earth land use, surveillance, for irrigation, for weather, such constellations are there, and they are used. This technology is also available because you are having the technology, you are having sufficient bandwidth, you are having fast calculations and good communication between satellites and the ground. They don't collide with each other, and yet they give us mankind the benefits. So these satellites will require very much less energy. So your ground stations need not be very powerful. Your transmitters from ground or receivers may not be very powerful. Things are easy. So such satellites are used, and such satellites are used for the cell phone network. Cell phone means our mobile phone. Mobile phone is a very small, tiny object. Even if you charge it, some mobiles they say they can be charged even if you wear them on your hand. So they require very tiny amount of energy. Their antennas are very small. They transmit very less signal. That signal is collected in your neighborhood somewhere, and from there it is directly sent to the satellite, or else it directly sends to the satellite from your mobile. So with such antennas at those frequencies, very tiny power is required, and it is possible because some small areas or small regions, you have a small that kind of a tower for the microwave region, and this gives you the cell phone network throughout the country. And depending upon the amount of usage, or where the density of population is high, where more mobile customers are there, you will need more and more towers nearby, because otherwise the signal will be saturated, the service will not be available. So you need a broadband towers in the microwave region for the cell phone network, and we see that the cell phone network is very successful. It is very efficient, and you can stream the pictures, huge bandwidth, you name it and it is available. So this is satellite communication, where again all the digital technologies use memories etc. are essential. Without that you can't work. And these cell phone network is itself another area where technologies are required, digital technologies. These all signals move in digital format. They are encrypted. We see to it that they are not stolen by others. And all such kind of networks are today possible because of the digital technologies that are available to us. And with minimal power, we can go for movies, pictures, entertainment, mm, n number of messages, and that is also so cheap. So such kind of things are possible in satellite communication because of the new technologies. Secondly, apart from these technologies, for these technologies we need highly coherent receivers. Coherent communication means the signal that is transmitted or received, the other transmitters or receivers, when the signal is very very tiny or small, if it is coherent, means the signals are, means the waveforms are coherent, means in the same phase and added together, then and only then lot of saving of energy is possible and lot of mm, more and more amount of communication is possible. So coherent communication technologies using a philosophy of PLL. What is PLL? Phase lock loop. So we know twinkling of stars. We also know the signals coming from satellites. The signals cross the atmosphere, the ionosphere, and so on and so forth. So the downlink and uplink frequencies slightly get disturbed because of these aberrations and disturbances in the atmosphere. Now that slightly disturbed signal, how to lock it? So if you have a phase lock loop, that loop automatically adjusts the frequency and brings it back to the proper transmitting and receiving within the given bandwidth. And that is done automatically without any human intervention. Then and only then you will have good communication between satellites. Otherwise, you have to spend huge amount of energy, very powerful transmitters, and your signal will be very very small, so bigger antennas. So coherent communication provides us this with phase lock loops, provides us, and this is a big science. You need inductance, capacitances, equivalent values, and lot of mathematics and lot of algorithms to uh, be able to have these successful applications. Optical fiber communication, this is yet another area which technology has made us available today. Optical fiber, few years back, optical fibers were not there simply. We could not control light. Now the optical fiber gives us the control over light. We can select a particular frequency. Using lasers, we can have a huge intensity of light. Using lasers, the quality of light that comes out through the laser is highly coherent. So such kind of coherent light, and with the advancement of optical amplifiers, means light is amplified as it moves along, and definitely it will need energy from some other bands or some other forms which will make this strong emission in that particular direction with that particular frequency or wavelength. Such optical amplifiers are not possible nowadays, and the communication should be coherent. So coherent PLL with a in the optical domain is a very difficult proposition, but technology has made it possible. We have surpassed the nature according to principles of physics. H cross, that is the Planck's constant, it is very tiny, 10 raised to power minus 34. But it is very small. Even then, it says that energy and time, space and time, energy and space, these kind of conjugate quantities cannot be very accurately determined. And therefore, in the process of emission of light, we know that when an electron is in a higher energy orbit, it jumps down to the ground state, lower energy orbit, and the difference between the two energy levels is emitted in form of a photon of energy h nu, where nu is the frequency, and corresponding to nu, you have a particular wavelength. Now, this wavelength is extremely small, 10 raised to 14 hertz. This is the type of frequency. And microwaves 10 gigahertz is 10 raised to 11 hertz. So, roughly 10 raised to 4 times means 1 10,000 times higher frequency. 10,000 times higher frequency means the equipment or the components for engineering for making optical light is totally different and handling the light. Second thing, we are able to control the intensity of light using optical amplifiers. Third thing, we have surpassed this uncertainty principle also. Whatever line width is there, because the atoms are moving and when they collide with each other, rotational energy, translation energy, polarization energy, all these kind of tiny amount of energies add, and instead of a sharp level we have got a band. Now within the band there is uncertainty. When the electron jumps down, that delta lambda is a very small quantity. At 10 raised to 14 hertz it has got small bandwidth, and therefore the line that is emitted is thick. So line has got a certain width. This is the natural width. It depends upon the speed of the molecules that are moving, and it also depends upon the temperature. But man has surpassed that. What we do in front of the optical source, laser source, we put certain cavities, resonant cavities, and we select a particular mode uh, for operation, and that mode is propagated, other modes die down. So one single photon of a particular frequency gets amplified, and coherent it stimulates other atoms to emit in the same direction, in the same at the same frequency, and therefore a coherent light is produced. So laser light is totally different from other emissions, and a coherent very sharp unidirectional beam is produced. Millions of electrons are the generated from one single, millions of photons are generated from one single photon emitted, and then this light is having totally different qualities, and we are able to select a particular mode out of that light also, and within the laser width also we are able to select, pick and choose and amplify that, and therefore with this coherent communication our quality of communication or amount of signal required uh, is reduced by thousands of times. Lesser signal, but you are able to communicate. So coherence optical PLL is extremely important, and within that we have surpassed the nature by having this kind of a selective line width. So selective within the laser also better and better type of. And then we have got another activity called a soliton. What is a soliton? Soliton is huge, pumping huge power into a small, specially limited, let us say, burst of light. And soliton is like a tsunami. We have heard about the tsunami. It created some deaths in on the seashore of Tamil Nadu few years back. Therefore, we came to know we don't have tsunamis regularly, but tsunamis are regular phenomenon in Japan, and tsunamis are also related with earthquakes under the sea. The water energy, different water waves uh, become coherent, and then this huge amount of water is displayed. displaced in the sea. Similarly, a soliton is like a tsunami, and such a huge amount of intensity of light burst or light packet we can send round the globe many times at a very high speed of definitely speed of light, and huge amount of communication is possible. So this kind of controlling light is possible today with the new technologies, with the different types of coherent communications. We know about optical fiber in medical applications. Now you don't have to cut a person. Endoscopy involves very tiny hole, and we have drug delivery personalized and delivery at the exact cell where you want in your body, and immediately very tiny amount of dosage will be required, and man will get better. So medical applications like sonography and others also, they we are able to put light into the stomach, try to see the object and bring the picture onto the TV for the doctor to see. Even remotely from here, there, from anywhere in the globe, you can consult doctors on video conferencing, and they can guide you in doing operations and all that. Robots are also used. So these all applications require digital technology, very fast technology, electro-optical applications in image processing and telescopes. Image processing, you take images, pictures of the earth, and as you know, your pixels, people talk about what is the pixel, what is the megapixel of your camera, or what is the pixel, megapixel or density of pixels in your screen, because that decides the quality of visualization what you see on the screen. So we are already talking about mega and gigapixels. So tiny parts on the screen, given the red, green, blue, whatever color mixing you want, and accordingly the color is available. This is all because of fast electronics, because of fast optics, because of high speed digital signal processing, calculating, giving a feedback, and making the system work. We have robotics in automobiles industry and many other industries, and we have talked about many other applications. We have drones also used for a military purpose and also for disaster management, also for taking care of floods, delivering food packets, also for entertainment industry. Drones are used. Also, drones are used for agriculture, spraying water, spraying silver in the clouds to get rainfall, spraying insecticide and pesticides on your fields. So drones have many positive and of course defense applications also. So we have tried to see that all these things are possible today because of fast digital communications. Now, what is the importance of fastness and calculation and getting a response, and only then our systems work. Say, I'll give two small examples. A satellite is a very tiny object. The very big satellite is a size of 10 by 10 feet room. Otherwise, tiny satellites, normal satellites are of the order of 2 meter by 2 meter by 2 meter, such kind of a thing. 4 feet by 4 feet by 4 feet, three dimension. So such satellites, you have to keep their weightless. You put them in the sky more than escape velocity. So you need devices to put it there in the orbit. Then a satellite is always moving. It is moving at a particular speed. You know the speed, but its speed may change a little. So that tiny object at your ground at a distance of 100 kilometers minimum and much more, geocentric satellite, huge distance, it subtends a very small angle in terms of seconds, not even minutes, very less angle. So If you want to communicate with the satellite, satellite is here right now, and after some time it is going to move there in the sky. It's going to cover a huge distance. Now, when you are communicating with the satellite, the signal come from there, it takes some time to come to you. Your electronics here processes it, makes a calculation, and when you send the signal, it should reach at that point, another point. So you have to point your antenna in that direction and send the signal in that direction. If within that satellite is exactly at that point, it is able to recover your signal. If the satellite is in this direction or that direction, little away, you will not be able to communicate it with it at all. So the time you receive the information about where is the satellite, the time you make the calculation, you have to find a speed, and exactly you have to pinpoint your antenna to the proper place. Otherwise, communication will not be possible because your amount of signal is going to be very less, and satellite has got not huge amount of good quality receiver. It receives whatever it gets. Its antenna is also limited in size. On the ground you can have the luxury of more power, low noise amplifier, super cooled amplifier. On the satellite these things are not there, but still we are able to succeed. We have been able to succeed with the use of technologies, fast calculations, and you know exactly where to pinpoint, and you send your beam. In communication, this is one part of the story. Similarly, another application I have talked here, I will show you a video also. That video link I am attaching here in this program. Whosoever wants to see can see. It that video was made some more than 10 years back by National Instruments, a famous company in instrumentation in the world, and that was for launching its product. What the product says, it is salting and measuring the ball bearings. For a industry, we make ball bearings. These are solid balls of some alloy, maybe steel, and these are made very smooth, and they are available in your fans also. You have ball bearings. In your automobile industry, everywhere ball bearings are used, and they are coated with some kind of grease so that friction is not there, and your objects can move on this ball surface very fast without loss. So if the balls get distorted or and damaged, their surface doesn't remain smooth, then lot of friction, lot of losses are there. So in mechanical systems, ball bearings become important. So there is a huge industry manufacturing ball bearings, and your ball bearing should last and last and last. It should doesn't get damaged. So these ball bearings, as they are manufactured in the industry continuously, they come through a conveyor belt, and they are allowed to drop down from a height of say 10 feet. So from a 10 feet at zero speed, if you send something, due to gravity, how much time it will take to come to the ground? 9.8 meters is the value of G. So half, 10 meters, half, 5 meters. It moves 5 meters in 1 second, because starting velocity is 0, ending velocity is 9.8 within 1 second. So you can take the average. So 5 meters it moves in 1 second. 5 meters is 15 feet. So suppose you are dropping it by 10 feet, you have got two-thirds of a second to do everything that you want to do with that ball. Now, as the ball comes out of that funnel and starts moving under the gravity, they have arranged the CCTV cameras or whatever image processing system to take hundreds of pictures or thousand pictures within this two-thirds of a second till it falls down. As it is moving three dimensions, all three dimensions, they are going to take pictures of this ball. Or if there is a light, you can take the shadow. And from those pictures, you have to make measurements of how smooth or how rough surface is there of the ball, how many dents or how many manufacturing scars are there on the ball. And then according to your calculations, you say if there is so many microns uh, holes or dots, I will accept it. So many microns, best quality. So many microns of damage, lower quality. And above 10 micron damaged, throw it. So you make some 8 or 10 categories for sorting, and you make 8 or 10 or maybe 2, 3, whatever it is. So in the number of bins, best quality, lower quality, quality 2, quality 3, and trash, throw it out. So what happens by the time this ball comes down, these 1,000 pictures or hundreds of pictures are analyzed by fast computation. These pictures also take time. A flash takes time to get a picture. We talk in terms of milliseconds. So within a second, easily 10 pictures, 1,000 pictures are possible. Ordinary cameras also. And then what you do? These 1,000 pictures you analyze, you make the measurement, you take the average, whatever your algorithm calculation software, and then finally take a decision where to put it in which bin. And accordingly, on the ground, like a weighing machine, there is something. On that, there is a plate, spring loaded plate, and by the time this ball falls on the plate, this plate, due to the power, due to the signal applied to the springs, this plate will tilt in different directions and reflect the ball. The ball will jump and fall into the particular bin, where according to sorting, whether it is good ball, bad ball, worst ball, or throwaway ball, good quality 1 to 3. So accordingly this ball will reflect to different places, and that sorting is done. This is humanly not possible, taking each and every ball and you doing mechanical hundreds of measurements and doing that. This is possible only because of contactless, good quality cameras with high resolution, making photographs, making fast calculations, and giving signal to the system to means reflect the ball wherever it is required. So such technologies are available today. You can see that ball bearing sorting thing, which was a product launched by National Instruments somewhere in 2007. So you can get the idea of the requirements. Similarly, optical fiber manufacturing, if you want to draw the fiber from a liquid, a seed is there, you go on drawing the fiber at a speed of few meters per second. Now you cannot take a piece of that, that is called destructive testing. You take a piece of that fiber and try to measure its diameter and all that. Fiber has to be extremely accurate in terms of dimensions, inner, outer, shielding and all that. Otherwise light will not propagate. So the conditions of reflection of light and refraction of light, totally internal reflection, will not be met, and it is of no use for communication. And communication requires miles and miles and kilometers of fiber. So fiber is drawn at a very fast speed. So without touching the fiber, you have to measure the fiber. So you use that lamp and scale arrangement using ballistic galvanometers in same third year of BSc, we did those experiments. Small charge flows, there is a coil, small charge flows, accordingly the coil tilts, and a mirror attached to that coil reflects, and you get a double degree, 2 degree. If it is tilted by theta, your um, spot of light moves by 2 theta, and at a large distance you get the leverage and you make a accurate measurement of the charge. So single charges are measured in this way in the physics lab using that lamp and scale arrangement, all taking hundreds of pictures of this fiber as it is coming out within a short time, and depending upon whether there is some damage or some problem, some correction is required, because the temperature of the furnace from which this fiber is drawn has to be within 1 millidegrees. Now what is 1 millidegree? Your accuracy should be very very much in controlling the temperature, otherwise the fiber, proper fiber, is not available. 1 millidegrees, to give you an example, our in our house our AC has got a tolerance of 2 degrees. If you set up for 25 degrees, it will allow the temperature to go up to 27, then try to come down. and then once it tries to come down, it will not wait at 25, it will go up to 23, and then it starts again going up. So this 2 degree tolerance, 2 degrees centigrade, and we are talking about milli-degrees. So that kind of control is required if you want optical fiber communication, if you want to manufacture the fiber. So these two things is a textbook knowledge. This textbook knowledge I am giving you, which is that book is printed at least 10 years back. This video of the ball bearing also more than 10 years back. So these technologies are available, but they were definitely not there 30 years back. Transistor was born in 1947, around that time. And since then, ICs later on, and now systems of huge ICs using microprocessors and controllers.